Hey guys, Ben Smith here with a video about recursive backtracking. Recursive backtracking is an implementation of a general algorithm known as backtracking. That's a lot of big words, but basically what it means is you go through and you say, this is a hard problem for whatever problem you're trying to solve. And you decide, instead of solving the problem all at once, I'm just going to use my best judgment and make a guess. And then you move on to the next step. And you say, wait, I still don't know what I'm doing, so you make another guess. And you just keep making guesses, and usually you come up with some logical order to make them in, which becomes important. And you make it through all these guesses, and you get to the first one. All the way through. You do all the first guesses you can make. And then you hit a dead end. You can't go any further. You're wrong. All your guesses were wrong, or at least some of them were wrong. And so you decide, well, all I can determine right now is that that last one was wrong. So you go and you undo that, and you go and you try the next logical guess for that position. And you try all those, and if they're all wrong, you try the next logical guess for the previous position, and try all the possible guesses from there. And this takes a while, but it does work. You eventually go through all the possible guesses, and you can get smart and do it better. And this is a very intuitive way to solve a problem. This is the way humans do it all the time when you're going through any problem. And a simple example is a maze. And say you're trying to solve a maze, very hard, and you think, you know what, I'm gonna do, let's say, the right wall rule. So you go through, and what the right wall rule ends up doing is it takes you through the first path on your right every time. And if it's a dead end, it just loops you around and has you take the next path on your right, going from the right. So it creates a logical order, and it goes through, and every time you hit a dead end, it makes you go back and try the next one. So it's a backtracking procedure. And these algorithms lend themselves very easily to recursion, because each time you get to a new step, you just repeat exactly what you did on the last step. Very easy. So Wikipedia here, they've made some pseudocode. And this isn't the pseudocode you'll find on Wikipedia. For some reason, to help make their pseudocode unreadable, which seems like the opposite of the purpose of pseudocode, they use one-letter variable names. So instead of candidate, they put C. Instead of parameter, they put P. And they don't even really say what these mean. I had to figure out what they meant by parameter and candidate. So candidate is essentially the latest guess. And the parameter is essentially the problem you're trying to solve. So you go through, and when you start with your candidate. Usually you start with the 0th candidate. It's just a nothing. And if you reject that, if you know that that's the wrong answer, that'll lead you only to wrong answers, then given the parameter, then you return. You go and you backtrack, essentially. And if you accept it, if given that parameter, that problem, and that candidate, and it's a solution, then you output it. And this is actually for finding all possible solutions. What I implement later finds a solution. And then you extend it. You take your guess, and you take the first guess. First is the first guess, given that parameter and that candidate. And you store it in extension. And if extension is null, that means that it's not possible and you need to backtrack. So it reaches the end and it backtracks. But if it's not null, you go through and you call your method on that extension, and it does all the same stuff. It goes through and it checks if that's wrong, it checks if it's right, then it extends it. And then once that is done, it either finished, it outputted something, or it needs to backtrack and take that off. And in this case, it can actually do both. It might output and need to go back and try more solutions, because it doesn't finish here, it only keeps going. And if you go through and you have done all those, then you switch your extension up with the next extension given that parameter and the current extension. And then you go through and you do all that again. And eventually this goes through and it hits the end and it returns. And then it essentially backtracks again, because this was most likely called from within this while loop in a different instance of it. Updates. Well, man, I love my code recommenders for Java developers, but can't do that right now. And I actually see this program, it outputs what it's doing as it's going, but it outputs too much to actually fit inside the console. So I use file output to remedy that. And then also I have this, this is a little confusing because you have to do this accepting and rejecting. And all these, the like next and first, I just roll it all up into the same method that returns a Boolean. And then this while extension does not equal null, and this grabbing the first and then the next. I just use a for loop that goes through every possible extension, and if this is true, it returns. Otherwise, it just goes on to the next one. And so my idea for an easy example is brute forcing the string hello by checking every possible string. It's incredibly stupid. There's no reason you should ever do this, but it's a really simple problem to teach it with. So you need a string for your output. You could also print it out, but I like having a string for it because then you can work with it. And then I made a helper method. So essentially all I do is here is just call that helper method. But I have this helper method here that makes a file to log stuff to. And then it runs brute force with a blank string. That's my 0th candidate I was talking about. And a log file to output stuff to. And then it returns the output. So this is a pretty simple helper method. Down here is really the meat of it. It prints the candidate because, well, it's pretty obvious why. I'm just documenting what it's doing. You ideally wouldn't want to do this because print commands are pretty slow, and just outputting stuff in general is pretty slow. You want to avoid it. And this, then it goes in. I switched up the order of accept and reject because it doesn't really matter, and it makes more sense to me to check accept first. And it doesn't make any difference to the running in this case, so it's fine to do it this way. It checks if the candidate is the goal, hello. So my candidate in this case is the candidate, and dot equals is basically my parameter method, and hello is my parameter. And then if that means that we've hit success, we've accepted it. So we output the candidate, and I return true because I'm only trying to find one, and that's what my Boolean does. And this is the reject from Wikipedia here. If we've reached the length of hello, but this wasn't already true, then we know we're wrong, because any more we add will just be going on forever, and we will never reach hello. So we return false. And then here's my for loop. This replaces the while loop with the first and the next, because that's really weird. And it just checks every uppercase letter. It goes from A to Z. And if you didn't know, you can operate on letters just like numbers on chars. And it makes just everything easier to work with. Really, they teach you, oh, A is 65, Z is, I don't even know what Z is, because you don't need to know. You can just write this, and you can do all your math with it. So I do that. And then here is my if statement I was talking about that I replaced the just raw call with here. And it checks if the extension is a solution. And if it is, it returns true because I just want to find one solution. Otherwise, it moves on to the next one. And this should never actually be reached. But Java wants it to be there because you eventually will reach hello. This is designed to always reach hello. So this should never get run, but Java doesn't like your Boolean method to have a possible chance of not getting run. If I do this and save it, it gets mad because it doesn't always return. So just put something like that at the bottom if it gives you an error. You could theoretically do this, I think. No. You could return true, but I return false because it makes the most sense. And then you can run this, and it takes a while to run because it goes through every possible string. Okay, it's done. See, it outputted hello, it found it. And then, like I said, it has this log file that it outputted it all to. You see, it starts with the blank string, and then it tries adding the first letter. It tries adding this A that it loops from. And, oops, and then that's the first candidate. And then the AA, it just takes another guess. AAA, another guess. AAA, another guess. And but that's not hello. But it is the length of hello. So then it hits this reject, because hello.length is now equal to candidate.length. So it returns false here, which makes it backtrack. And you see it takes off that A and it puts a B. And then from there, that's also wrong, so it puts a C. And it does that through the whole alphabet all the way to Z. And then it pulls off this A and puts a B. And then it tries that through all the alphabet. And it does this, and it goes a very, very, very long time. And eventually, it makes it to hello. You can see, it's a lot of combinations. It's at 3 million. So, don't do this. This is not a practical use of anything. But it is kind of funny, and it's a good way to teach it. And this example, it kind of helps you get the gist of things, and there are a few things I'd like to touch on it. You see here, I have this candidate plus C. It's somewhat intuitive to do it like this, to have your extension, and you say, you know what, I want to modify my candidate. I want to do candidate plus equals C. And then that adds it, and then you have your backtrack here. Here's where you do your backtrack, and you get all excited. You do your candidate equals candidate. You essentially chop off the last character of it. And this seems like a great idea. You chop off the last character of it because that's all you added. But the issue with this is that you've got pass by reference, not value going on here. So as soon as you get in, you make this call, and it goes through, and it adds its own letter. And then whenever it returns, it doesn't remove that letter sometimes. So then it just keeps adding more letters. You can see this doesn't work. What? Okay, it didn't work earlier. Bad example. Okay, this is a valid way you can do it. I'll just edit this out. But you gotta be somewhat careful with this. Strings are really bad at demonstrating this kind of thing, because strings really like making new strings. But candidate plus C works. So just do it that way. This is a stupid example, so I'm going to show you a better example, the 8 queens problem. This is a problem, it's in chess. And in chess, it's pretty simple. You have a board, and you have your different pieces, and they can capture each other. The game itself is pretty simple. The strategy gets really complicated, but you can learn the game pretty quick. But the basic concept is that pieces can capture other pieces, and you want to get the king. We don't care about any other pieces, we only care about the queens in this problem. And the queen is the most powerful piece in chess. It can move along both horizontal and vertical, and along the direct diagonals, because the chessboard is a grid. It can't move on anything with a different slope than that. It just moves along the straight diagonal. And it can capture anything. It can kill any piece that's on any of those spaces. So this problem is essentially take an 8x8 chessboard, that's the standard size, and put 8 queens on it in a way that they can't capture each other. And here I represent the board using a 2-dimensional integer array. And that's initialized here. And then I have my main method, which just calls my backtracking method. My backtracking method, it finds a queen solution given a board to work with and the amount of queens currently placed. And it starts off with 0 queens placed. Here it prints the queens, which is kind of long because it has to print a 2D array and do custom stuff with it, because I print queens, invalid spaces where I can't put a queen, like where a queen could capture, and dots, which is an empty space. And this looks pretty nice when I print it, so I do it like that. And then it puts an extra line at the end to separate the boards out. And here I have my base case. This is the success of the problem. This is the except from above. And this is if you have placed 8 queens on the board. And so you just output the solution, and then you return true. And if you don't meet that, you start placing the next queen. And the way you place your next queen is by going through, you start at the row of the number of queens, because the way I do it, I work down from the bottom of the chessboard, and I put a queen in each row. And so I start at the very top row, which is the 0th queen to place. And so I put it down, and I do that by going through each possible space in the row, and if it is 0 in the array, and up here I say 0 is nothing, that's an empty space, then I make a copy of the array. And I have to do this because of the way arrays work. You can't copy a 2D array directly, you have to copy each individual array, because it's not an array of arrays, it's an array of references to arrays. So if you make a copy of it, it's a new array with a new reference itself, but it still is an array of all the same references to other arrays, so it's still mutable. This is just an easy way to do backtracking. Rather than doing a reset, you just make a copy, and that gets deleted when you reach the end down here. And then I go through and I set that spot that I just found to a 1, you see in the num queens row and the jth position. And then here I iterate through and mark every space in that column invalid, and I mark every space in that row invalid, and then I mark all the diagonals invalid. And then I do my if statement here with my new array, and I've added 1 to the number of queens because I want to place the next queen. And if it's true, I return true, and otherwise I just mark that position I found invalid because I know I can't put a queen there. And if the entire row is invalid, if it makes it through this entire for loop and doesn't find a solution, it returns false. This runs much faster than the other one because it's not terrible code. As you can see, it puts down a queen, then it puts down another queen, puts down another queen, puts down another queen, puts down another queen, but now every space on the board is blocked. It can't put the last 3 queens down. So it backtracks, and it puts the queen in the next possible position. And there it has some extra spaces, but because it wants to put 1 in each row, it quits, because that's not good. So it backtracks more, and it backtracks and stuff, and eventually it'll pull up that second one and put down, and put it in a different place, as you can see. And then you come all the way down here, and it found a solution. 1, 2, 3, 4, 5, 6, 7, 8 queens on the board. None of them touch each other. You can check that. This is a solution. And it's the first solution it found. You can make a list of arrays or output only the solutions, because, like I said, printing stuff is slow. So you could only print the solutions, and it would be easier. And then rather than having find a queen solution, you could just find queen solutions. And this is a pretty simple method, really. the longest parts are just marking stuff as invalid and printing it. And it looks a little daunting at first, but you should have the tools to understand it. And if you want to look at this code, I will have this file in the video description. And I will have this file. This one's kind of big and not really very useful, but if you want it, you can just run this code. And it kind of lags the computer, so I'm going to close it. But this backtracking procedure, my readable version of it will also be there if you think that's helpful. And other than that, you should have the tools to understand this code. It's really not that hard. Recursive backtracking sounds big and scary, but as long as you just understand that it's just making a guess and then trying the same thing on that, you're good. And here the incrementation helps with tracking the number of queens. Over here we track that incrementation using the length. So you always want to have something you're incrementing so that you can easily deal with stuff. And I actually use this, you'll learn more about what Enigma is, but I use this to write a program that would help crack Enigma. And it cracks the pegboard using recursive backtracking, and I don't expect you to understand any of this. This is disgusting code too. It has all kinds of timing stuff that I didn't take out. And it doesn't even work. It didn't work, but got close to working. And I like it, so I'm going to show it. Okay. This is the awkward silence at the end of the video because I don't know what the outro is going to be. Okay.